See a few folks joining me on YouTube. Thanks for coming today. Great to have you joining me for our very last lecture of COMP2300. Seems like my microphone's all working fine. Signal is hot. Recording and streaming. Make sure I got my interface up. Get rid of Chrome. Prop a slide up and almost ready to kick this off, folks. Thank you very much for joining me. So great to have a live audience. Here we go. G'day, folks. Welcome to week 12 for COMP2300. Thank you so much for joining me live today, those who are in the chat and on YouTube and on Twitch and on Microsoft Stream. Hopefully we pick up a few folks over the next few minutes. It's an exciting day for me because this is actually going to be our very last lecture of COMP2300. We have certainly had a big journey this semester exploring the microbit, a brand new board that we've been working with for this very first semester. So it's been new for me, new for your tutors, and of course new for you who have been learning all about how to use it. Life with your microbit has probably been pretty exciting for the last few weeks because you've been working on your assignment. And I'm so pleased that folks got their assignments in on the deadline. Thank you so much for getting that to work. I know that it's a very busy period in week 11, week 12. I'm just checking my screen here on my stream on my second screen. It looks like I exist. That's good. I am giving my lecture. It's good to have that. I'm going to close Teams over here because if it pings here, it's annoying. Get Teams up on my other window. Yes, week 11, week 12 is very busy. Thank you, especially for those who are choosing to join me here in week 12, even though I'm aware that many folks have other assessments coming online. But it's good to have this lecture anyway, whether people are watching it now or if they're watching it later, because this is going to be your summary, really, of all the stuff in this course, which is the kind of thing we look at in our exam. All of the topics that we've studied, remembering some of the old ones and coming back to some new ones, just to give you a bit of an overview so that you can get all these topics together in your head and start your revision process. So I realize while folks are working this week, you may feel like you want to get your assignments done first, but it's good to have this lecture in your back pocket so that you can come back to it shortly when we get to the exam period, which starts next Thursday, I believe. So, a little bit of admin. Folks, assignment 2 is done. Congratulations on getting that together. I haven't looked at any yet, would you believe? We still went through a process of cleaning up a few loose ends related to folks needing extensions over the weekend for various things that were going on, and then making our big mega fork of all of your assignment repositories so I can get them out to be marked. I'll be having a look at a few tomorrow to start our process of marking, which will take 2 weeks. But I just wanted to offer an unconditional congratulations before even seeing your assignments, because it's always impressive when folks meet a challenge like we set you for assignment 2. You still have one more lab this week, and lab 12 is a doozy. It's our make your own operating systems lab. Would you believe that last year this used to be 2 labs, but I've made it 1 this year because I think all of you folks are ready for the challenge of doing it in 1 3-hour session. Don't skip this lab. I know that there's other stuff going on this week, but make sure you do attend your lab session and get these lab tasks done. Remember that you do get marks for these labs if you complete all your lab tasks, and the last lab pack, labs 10, 11 and 12, is due on Wednesday the 1st of June by midnight, before midnight AEST. Folks, you're getting a good amount of extra time for this one, so I'm not going to be handing out extensions for this just because folks are disorganized, but I really would like to see that everybody is getting as many marks as possible out of this one. Basically, I would love to give full marks to the entire class for all of the lab packs. It hasn't always been that way because I know that some folks get busy with other things or things go wrong, but really we should all be aiming for full marks on the lab packs, which means that you've at least attempted every task. Quiz 2, I've reopened actually. There were some people who missed it in week 10. If that's you, go do it now. It's in Wattle. It's open, I believe, until the end of this week. Again, this is something which I really want everyone to get full marks on. It's not supposed to be hard. It's supposed to be a challenge that you have to do a few times to get those marks, but it does tell you the answer eventually if you get it wrong enough. So you can put the time in and get that mark to add to your final grade so that you just get that one little mark up. It could be the difference between a grade point for you. So think about it that way. Final thing, prepare for your final exam. We will have finished the lab pack by the exam period. I haven't set the final exam yet, so I don't quite know what's going to be in it, but similarly to the mid-semester exam, I will be providing you with some material to look over that will help you to attack a big significant question in there. I would be using the mid-semester exam as your model for what this exam is going to be like. So I would not be expecting coding questions. I've already had you code. You've done a lot of coding for me in your 2 assignments and all your labs. I don't need to see more coding from everybody. So what I would like to see is your understanding of how a computer works overall and of all the different topics that we've studied in this course, as well as, in particular, your understanding of really what's going on when assembly code runs. And those were those tough questions in the mid-semester, really understanding what a block of assembly code is doing and knowing how every single part of that little clockwork mechanism fits together. So expect a few challenges like that. Mainly expect questions focused on the topics we study in lectures and you get extra training in through labs. And we're going to talk about that today as we go through our tour of the topics. And then the final exam is, in fact, I'll just look at our assessments page. That's our last assessment that's left. Everything else has got a tick on it. Well, I suppose lab tasks 4, there's a partial tick there. But final exam is the last one. So when you get to, well, for most of you, you've done almost 70% of the assessment for this topic. So you can feel really good about yourself, actually, that you've done so much work already. Final exam's on the 11th of June. It's a weird time. It's a Saturday, would you believe? The exam starts at 5:40 p.m. on a Saturday. I didn't know that I'd have to be working on a Saturday night for you folks, but I guess that's what I'm doing. So the exam is 150 minutes in length. It's not a giantly long exam. It's a 2.5-hour exam to give you plenty of time. It will be longer, half again as long as the mid-semester exam. Let me put it that way. Mid-semester exam was, I think, 8 questions. So maybe this is going to be 12 questions or thereabouts, something like that, to get from 20% to 30% of an exam. And you've got that extra amount of time to help deal with it, a bit extra than the half again. It's again a Wattle exam, so you should have plenty of experience understanding how to do a Wattle exam at this point. The procedure will be the same. Please record your screen. That could save you if some work for some reason is lost, which very occasionally happens in a class of 400, maybe once. So there was one person who was happy they had their recording going. Let me tell you that. Back to our lecture. Let's get through this tour of the topics. Folks, it has been a big journey. I don't know if you remember what things were like when you started this course, but you maybe had never seen a line of assembly code in your life, and you just didn't know what to expect in this course. But you certainly know now. You've written significant programs in assembly programming on the bare metal, and that means that your program runs directly on the CPU of your microbit without any libraries, without any operating system. There's nothing between you and the raw power of the CPU. Someone's got crying face Saturday. I know, I don't make the rules. Exams get scheduled by Central. Yeah, I know Saturday is a yikes, but it's just the days that the exam folks choose. Don't know what to tell you about that. Wish it were different. Is my little drawing thing working? So what do we actually do in this course? What was this course about again overall? It wasn't just about assembly programming, right? Because we did a lot more in our lectures than just assembly. Really what we're doing in this course is using assembly to teach you a lot of really important topics to do with computer systems as a field. How does a computer actually work? There are three big mega topics here. Computing instructions, this one, the high-level thinking to assembly part, that one, and the interacting with the world part here at the bottom. So what are in those three big mega topics? Well, in the computing instructions one, which is really how does a CPU make stuff happen at all, we had two topics. One was digital logic, the other was the hardware-software interface. Then in our high-level thinking to assembly area, we had three topics: functions, data structures, and control structures. Those are the three fundamental parts of programming that you will have learned in your first-year computing courses and continued into courses like COMP2300, which you now will have practiced and seen how that translates from a high-level programming language down into assembly. And then we had our four topics to do with interacting with the world. How do computers work in the world in context, and what does the computer hardware do which makes them work? So we had our four big topics here were, oops, I'll get my red pen out, architecture, operating systems, interrupts and asynchronism, and networks. Yeah, the Power Four, the Fantastic Four. So these were the topics where you had to have a really good understanding of everything above here to see why the hardware was designed the way it is in order to get these things to work. When you understand these things, you can understand these things down here. So that's why these were the last 4 weeks we've done. That's week 11, week 10, week 9, and week 8. That's week 8, yeah. 9, 10, 11. What was this? That was 7, 5, 4, 2, 3, and 1. And week 6 was a bit of an extra topic week. We're going to go through all of these little bubbles in order, starting with digital logic again, starting with all the way back to what we did in week 1. What did we talk about in week 1? The digital logic topics. In short, Boolean algebra, combinational logic functions, I think. Not combinatorial. Who wrote these slides? Classic mistake. It's not combinatorial logic, it's combinational logic. Digital electronics and logic gates. Learning a little bit about how electronics works. Looking at binary encoding and 2's complement and number representations really in assembly, number representations inside a computer. We made a ripple adder, half full ripple carry adder. We talked about all of the things in an arithmetic and logic unit that would go into a CPU. And then we finally concluded with this basic CPU architecture. Things we didn't talk about, which aren't in this course, we didn't talk about float representations. We could have, but we didn't. Nope, didn't do that. I guess we didn't learn about that. There's a thing called Karnaugh maps, which lets you develop combinational logic truth tables from combinational logic functions. Didn't do, I don't know, whatever it's called, K-maps, car something maps. So it's so much on the course I can't even remember how to say it or what it is. So you don't need to know that. Another thing about digital logic is that most of these topics were already assessed in the mid-semester. Mid-sem. Didn't do CPU architecture because we're saving that for the final. And this one in particular was in the mid-sem. This one is a whole of course topic, number representations. So you can expect a question in your exam. You could expect a question related to how numbers are represented in assembly. That's like a whole of course topic. You could expect questions about CPU architectures, but all the other logic stuff, we've done it. So I'm giving you an overview here, but we're not going to spend much time on it because I've already assessed it for everybody. We had our logic gates. You remember that NAND and NOR are the universal logic gates, and we found that they were the kind of logic gates that you might use if you wanted to build the glue logic of a computer last week when we were looking at the replica 1. So there were a couple of NAND chips on that computer which were used to generate the correct signals or calculate the correct output from a number of address lines to select different chips. So all of the elementary logic gates can be built out of NAND, as it's written in these diagrams. We talked a lot about the ripple carry adder, and there was a good question about the ripple carry adder in your mid-semester exam. So everyone knows about that. Mid-sem exam has assessed this. Well done. We talked a bit about 2's complement representation, a bunch about 2's complement representation. And our basic idea of this was to make sure that we would define binary negative numbers so that our ripple carry adder works with them. Basically, we need to have something organized so that if you have whatever the representation of 42 is, plus the representation of minus 42, you end up with 0, or something which can be interpreted as 0. So to make a negative number negative, what we ended up doing, if you go back to lecture 1, we worked out that the way it must work is that you invert the bits and add 1. If you just invert the bits, 1, 1, 0, 1, 0, 1, 1, and you add it together, you're going to end up with 1, 1, 1, 1, 1, 1, 1, 1. And if you want that to be 0, you're going to have to add another 1. If you add the 1, that ticks everything across to 0, 0, 0, 0, 0, 0, 0, 0, 0, and you end up with a 1 in the carry bit. That's the C. So there's really only one way to define binary negative numbers so that our regular adder is going to be able to add a number and it's negative and end up with 0 with 1 in the carry bit, which is to invert the bits and add 1. And that's how 2's complement works. Crucial idea in computing, to make our adders simple. Not always the case. There are other kinds of adders that could handle, for instance, the 1's complement system, but they have to have different compromises or different ideas about it. Flip-flops. We didn't talk a lot about flip-flops, but we understood that these are the elements of computing which allow us to create memory in a simple way, registers, and things like counters and timers. Again, this is not a huge part of the course, similar to the ripple carry adder. It's something which is there for your knowledge, but I would consider this assessed already in the mid-semester and through your labs. I'm not going to assess that again in the final exam. I know I didn't have a specific question about it, but I could have. A few thoughts about digital logic. What's the difference between Boolean algebra, combinational logic, and sequential logic? And why do we need all of these things to describe computers? Well, I guess the concept of combinational logic, this was about our logic functions, right? F of A and B equals a bunch of stuff with logic symbols in there. Boolean algebra was our way of taking an equation or a sequence of terms in logical values and manipulating them in various ways. Combinational logic was allowing us to have functions, and that allowed us to build the adder, let us calculate things. Sequential logic allowed us to have memory, so we really need sequential logic to cope with the concept of memory in our systems. Why do we need all of three of these things to describe computers? And are there parts of this story missing from COMP2300? So these are questions. Oh, thank you, Adnan. Says, honestly, this course's two's complement explanation was the best I've ever seen. Well, it's only taken me 4 years to be able to do it, do it properly in one go since I started teaching COMP2300. At least I didn't have to do the floating point explanation, IEEE 754. Otherwise, that will take me another 4 years. You know, the best way to learn something is to teach it. So I've really been developing my explanations for some of these things over the years. Why do we need all these things to describe computers? Are there parts of the story missing from COMP2300? These are things which are final fodder. They're final exam kind of questions, because your final exam, one of the learning outcomes it examines is how you can travel between levels of abstraction within computer systems from the very high level programming languages, operating systems, networks, all the way down to digital logic. So I'm probably not going to ask you specific questions about flip-flops, but there could be a question asking you how to describe a computer in terms of digital logic circuits, which is this kind of zoomed out high-level ability that we're training you to do in COMP2300, to look at a computer and see all the way down to NAND gates. I'm going to keep moving because we've got a lot of topics to get through. CPU architecture, we did a little touch of this in week 1 and week 2. What are the main components of a CPU? Can you explain what each component does? We come back to this in the architecture part, but I've had folks who have memorized this diagram and reproduced it for me in the exams. I don't really want you to do that, but I want you to be able to write about it. Any part of this diagram, you need to be able to explain to me what it's for and why it does its job, and why we can't live without it, and if we had to, what we might do. Those are the kind of questions I like to ask, some speculative computer design questions. Hardware-software interface. One of my favorite topics is starting to demystify how a CPU gets work done. And wasn't it exciting to get through this, to start to see how we could store things in memory, how we could do little bits of arithmetic, and how we could form an if-then-else with the condition codes and the CPU status flags, and the realization that everything on our computer works this way. This is how it all fits together. Every time you write a program in Python, Java, TensorFlow, PyTorch, it's all this stuff, just happening really, really fast. What's the structure of a computing instruction? How do we translate assembly into CPU instructions? The kind of manual assembling of assembly lines of assembly, what do they call it? Mnemonics into a machine code. The CPU status flags, the ARM v7 instruction set that we learned from our reference card, loading and storing from memory, and branching. So what about the NCZV flags? Negative, 0, or NZCV, yeah. I always mess up the order. Negative, 0, carry and overflow. Well, the negative flag, we know this very well, that anytime the output of an ALU operation is negative, as if interpreted as a 2's complement number, the negative flag is set. And that literally means that if bit 31 is set, if bit 31 is set, n equals 1. This is on the assumption that s is set, if s equals 1. That means we're setting flags. Don't forget the s. So you have to be doing a subs or an adds or a flag setting operation. If bit 31 is set, the negative flag is set. So the negative flag is the same as bit 31. You could imagine it in a CPU design having a little wire that literally connects bit 31 of our register. 30, 30, 29. These are coming from the ALU. And just a little wire here connecting N to bit 31. Sorry about my crazy pen going crazy there. The 0 flag. This status flag is set when the result of an ALU operation is 0. So if you took all of your numbers, 0 to 31, and you ANDed them all up, and you get some operation here, you might end up with the Z flag, or not Z flag, right? Because if you're ANDing them all up, wait a minute, you're ORing them all up, not ANDing them all up. If any one of those numbers is set and is not 0, you're going to end up with a 1. If they're all 0, then your Z flag is going to be set. So not Z equals all of these numbers getting ORed up together. Carry flag. So this is simply the value of that carry output on the ripple carry adder after doing a addition operation. So something like this, mobs R2, OXFF all zeros, mobs R3, OXFF all zeros. That's going to be more than 32 bits, take more than 32 bits to represent that number. That means we do need the carry flag to be set. There's going to be a 1 in that C output. And the overflow flag. This was one of the harder ones to expect, but the rule for the overflow flag is if you've got a positive number, if A is positive and you've got B positive, and your output of A plus B is negative, we know that something's gone wrong. So that means A being positive means that bit 31 is 0, bit 31 is 0 for B, but bit 31 is 1 on A plus B. So that means that we've gone too far in the positive range of our 2's complement number range. Remember, when you go into 2's complement, you only get half the number range to be positive and half to be negative, or you get one extra negative number than positive numbers because 0 absorbs one of the numbers in the middle. So if you've got A plus B ending up negative, that's bad, and that means that V is set. Similarly, if you've got A is negative and B is negative, and you've got A plus B being positive, that's also bad. That's also clearly wrong, right? A negative plus B negative, it's got to be a negative number. It can't be positive. That's also bad. That means that V equals 1. So I'm explaining this in the specific implementation way that these things work, not the interpretation. So you can read the interpretation and make an assumption about how it should work, which would be wrong. But the actual implementation is if you have two positive numbers and you're trying to add them together and bit 31 is set in the result, the V flag is set. If you've got two negative numbers and you're trying to add them together and bit 31 is 0 in the result, V equals 1. So it's a very specific implementation because this has to be little wires connected to little NAND gates. It's not like some magical list of things written in text. It's little wires in NAND gates making this happen. Okay, we'll deal with questions later, but I want to keep getting through topics because that one, NZCV is something that you really need to keep trying on your own. There's a lot of questions about it in the exam collection. The memory map. Remember the memory map. Ooh, remember. Remember our code lives in everywhere up to OX2. And starting at OX2 is our free RAM zone where we can start saving data, making our arrays, making our data records. Then we've got our fun peripheral zone. This is where all of our LEDs work, And remember that all of your OX4s, I think your LEDs are OX5s, and a bunch of OX4s are some of the other peripherals on your microbit. Someone's asking me a question. Good question in YouTube. If it was tested in mid, will it be tested again in final? I will provide some detailed information about that and particular information about some parts of the exam when we get to another slide about all of the stuff. But I think I'll probably write a big post about this on Piazza, hey, because it's information that everyone needs to know. I'm specifically not going to ask more questions about low-level flip-flop stuff. We've already done that. So what I specifically will ask questions about is everything since the mid-sem. What's that? Data structures, networks, interrupts, operating systems, architectures. I will also be continuing to examine specific knowledge about how assembly programs work. So your mental model for how an assembly program makes a CPU do certain things, you need to keep knowing that. So expect more questions about those ones. But I mean, broadly speaking, I'm not going to ask any questions again from the mid-semester exam. I'll ask more questions, but they'll probably be more related to the stuff we've done recently in the course, not stuff you've already that's already been completed. Where was I in the memory map? Oh yeah, we've got our I think the vendor-specific memory is where all of the Cortex M4 stuff lives. And remember, we've got our 4 GB address range here. OX0 to OXF is 4 GB of space, but we don't use all that. They only use tiny slivers within this whole space, all wired in with little NAND gates to select different places that the addressing system should point to. We had our rotations and logical shift operations. Hopefully these are things that you've used as you've gone along in your journey at some point to make things do certain things. You've probably all used these kind of shorthand notations in assembly, like OB1, left, logical shift left, 21 or something to select pin 21. So you know how to do that in assembly. You probably know how to do it in C, but I hope that you've tried it just with the actual assembly instructions. If you go into the exam not having tried all of the assembly instructions on your reference card, you're doing it wrong. So go back, look through the reference card, and make sure you know what every single instruction does, because they're all important and useful, and probably I'm going to assess ones that we've seen already and ones that you haven't seen before, or haven't assessed since the mid-semester. But all of those assembly instructions, I expect you to be on top of. Some of these instructions I'm not sure have particularly good uses. Again, I'm never quite sure about RRX. What is that? Rotate right and extend by 1. It's a sort of way of kind of doing a 33-bit rotation, which is an odd thing to do. Haven't found. I know someone said you can. It's a 33-bit rotation. I know, but what would I ever use a 33-bit rotation for? Haven't seen it in an algorithm where it's crucial to have RRX. Remember that ARM is load store, so all of your instructions on your reference card are either an ALU operation that takes inputs and saving outputs to registers. It's always connected to registers, or they're a memory access operation. So when we looked at the 6502 assembly last week, remember there was the ADC command, which could have add with carry. It actually takes an address as its, or it can take an address as its argument. So it can be add with carry 0300 to point to memory, which will take whatever is in 0300. It's going to use the dereferencing operator from C to say what the value of 0300 plus whatever's in the accumulator, and it saves that into the accumulator. Someone's telling me, Nick knows everything. RX is useful in multi-word division algorithms. Well, that's useful, isn't it? I think I'll ask a, shall I ask a final exam question about multi-word division algorithms? That seems a bit mean. I think I probably won't do that. So this operation in 6502 land, it did a plus and it also loaded something out of memory. So it's loading out of memory and it's doing arithmetic. We don't do that in ARM. No, no, no. We do our letter, R1, whatever is in O300, right? And then add R0, R1. So the ARM ISA has always separated loading things from memory, do that in one CPU cycle, and then you do your arithmetic in another CPU cycle. It's not smushed together in one operation. What does this mean for the programmer? Well, if you're writing in C, it doesn't matter at all, but if you happen to be writing in assembly, well, it does mean that you've got to always be loading into your registers and then storing backwards. So you often have this load, twiddle, store, load, do something, and then store, add, sub, LSL, LSR, the load, twiddle, store, what's it called? A pattern, yeah. Load, twiddle, store, pattern. And we saw this when we were trying to set up some of those peripherals. I would have, in the lecture demos, have 100 lines of code, which was just load something, set something, store something back, load something else, set something, store it back. Those little three-line couplets over and over again. Whereas a triplet, not a couplet, that would be 2 lines. Because 2 is a couple. Loading and storing. I think you folks are very adept at this stuff now. Our load operation, just with standard one single address, you'll have done this 1,000,001 times. I'm really pleased to see how much people are using memory now. I've noticed that in previous iterations of this course that folks didn't use memory enough, and I think I've changed the course enough so that you're really forced to, and it's been great to see. What about our funky extra loading and storing operations? Letter B, loading a byte from memory, letter H, loading a half word, and the store operations of those. There's some other, if you look in the manual, there's so many loading and storing operations. Just tons of them. There are ones that pretend to be unprivileged. If you happen to be in a handler and you want to do an unprivileged load, I don't know why, but to see if it works or something. I wouldn't know why, but you can pretend to be unprivileged. There's just squillions of them. This is what happens in a load store architecture. You get so much detail within the loading and storing operations. We also had these ones that you've used a lot now, push and pop, and the store multiple decrement before and load multiple increment after operators to give you a negative stack, help you to make a stack work. And go back in the lectures and relearn how those things worked, because it was kind of fun to see how we encode all our possible registers into a push instruction. How does push work? The answer is in the lectures, and it's in the manual. Fun instructions. Well, I'll tell you a little bit about it. The reason push works the way it does is that it's simply got a list of bits, 1 bit for each possible register that can be pushed. And so you don't get to choose the order that those registers are pushed. They're always pushed and popped in the same order, because the instruction can only store which ones are being pushed, not the order that they're being pushed in. So it doesn't matter which order you write them within these braces. It's just going to do them in the order that the CPU is set up to do. And conditional branching. This, folks, I think it was a turning point in the course when you learned to do conditional branching, because it meant that you could do so many things. You could do if, you could do while, you could do for, and suddenly you were not just using your computer as a little fun calculator. You could write programs. You could write programs because it meant that you could put your structure in. Structured programming is the important course you took last year, COMP2300 which taught you really what programming is within most of our computing systems. And the conditional branching is how you made that work. So this was the classic list: branch if equal, branch if not equal, branch if carry set, branch if carry clear, branch if negative, branch if positive, branch if overflow is set, branch if overflow is clear. These are the conditional branching operations that only rely on one condition code. Whoops. We probably have some, if I just go to the resources page. Oh, that doesn't seem good, does it? I really need my website to work, otherwise I won't be able to show you any slides. Oh, what? Don't give me that, Firefox. I'm not restarting. We know that you've got these ones that only have one condition code, but there are also many that have multiple condition codes from your reference card. You need to practice those ones as well. And those ones are the tricky ones that I'd probably ask in a question, aren't they? Back to our big list of topics. Someone asked about what the exams, what questions are going to be in the exam. Classic question to ask. Well, I would say that the questions are mainly going to focus on the stuff we've done since the break: architecture, operating systems, asynchronism, networks. Now, that doesn't mean I can't ask questions about the dependencies. So I could ask questions about architecture, which requires knowledge of digital logic because it uses digital logic and requires knowledge of the hardware-software interface. I could be asking questions about operating systems that requires knowledge about functions, or data structures is also in there as well. That was something we did since week 7. What was that? 7, 8, 9, 10, 11. Functions and control structures are used by all of these things as well. And, just these high-level thinking in assembly is just sort of a basic understanding of the course. So you can see that my questions in the exam are going to focus on the new topics, but the new topics build on the old topics, so you have to know that stuff too. So I'm not really giving you any out-of-jail-free cards here, because the whole course since the mid-semester exam has built on previous material. And someone says, to what extent do previous exams reflect the final exam content this year? I don't know. What does that mean? I'm supposed to tell you that I'm asking exactly some question? I think what I said last time was look at the 2020 exam, which was the one I set as a guide. The 2020 exam is most authentic to me. 2021 exam was written by someone else. I suppose I wrote the 2019 final exam, so you can look at that too. 2018, 2017, written by someone else. There's exams evolve over time. I will ask you questions that are to do with these exams because they're based on the same material, the same concepts. But as I said before, I'll provide you with some more specific guidance about the exams when I'm just about done writing it. Another question from YouTube: are there answers for past exams? No, there are not. You have many of the 2020 questions, or the 2020 multiple choice questions are in quiz 2. So you've already done that study. I've forced everyone to study for the multiple choice questions. You've already done it. The past exam answers don't exist, actually. So particularly 2021, if you ask me a hard question about 2021's final exam, I might not even be able to answer it. Some of that stuff was pretty wacky, from my perspective anyway. Made sense to the lecturer last year. Functions, big topic. There and back again, our big journey, BL to BX and and the link register. Understanding the stack, still something that trips folks up. Knowing how the stack works. Calling conventions, functions calling themselves, recursive functions, local variables and the stack frame. Relative addressing, passing values by copy and by reference. These are super important topics about knowing how to program. There and back again, over the hills and far away. And remember that a function really starts with a BL in your original code, and the BL takes you on a journey to a label, right? Function, and then you do some instructions. At the end of that, you've got your BXLR, which takes you right back to that very same spot, or the very next line. Oh yeah, if there's any past exam that asked you about macros, well, I'm obviously not going to tell you about macros. It's not in the course. Yeah, macros are dead. Like, folks, in general, like, study the things I'm telling you about, and if you're looking at past exams and not listening to my lectures and not doing the labs, you're probably also doing it wrong. Because, like, I don't read the past exams to decide what to talk about, to examine you on. I think about what I've taught you and what I've taught you through the labs. So study that stuff. I don't think there's anything else in those exams. I'm just trying to think about any topics that we haven't done. We've gone into more detail in networks related to UART. Is there any Haskell covered in the final? What? Why would, what? Why? Why would I ask you about Haskell? That's really confusing. Sorry, I'm just taken aback from. I'm gonna have a break because I'm so shocked by that question. Why would I ask you about Haskell? Yeah, well, if I was to ask you a question about Haskell, folks, I would have to first remember Haskell because I haven't written a program in Haskell since 2005. So I have known about Haskell in my life, but not in the last 17 years. So let me put it that way. I hope I don't have to teach COMP2300 next semester. What was I saying? The PCS, oh yeah, the ARM v7 procedure call standards. The most important thing in this standard was really like the purpose of different registers, or what you can expect different registers to be used for. And really, ARM only uses these 4 registers as being special: PC, LR, SP, and IP. We never use IP. We really only have these special ones: SP, LR, and PC. And recall that R0 to R3 are the ones that a function or a caller is expected to save and not overwrite. Anyone can use that as scratch registers. If a function is using those registers, they could be overwritten. R4 to R11 are the registers that a function needs to save. The callee, or the function running, needs to save those registers if they're going to be overwritten. Sometimes we have used R11 as a frame pointer, but you'll know now from your C lab that GCC likes to use R7 as a frame pointer because there's no standard frame pointer in the ARM architecture procedure call standard. The reason GCC uses R7 is because in an older ARM, the ARM thumb ISA, you didn't get to use, or there was a limitation on the higher numbered registers. The lower numbered registers could be used for a stack pointer for doing the stack operations. So GCC got into the habit of using R7 to do those stack operations as a frame pointer for that reason. It's a historical reason. It's not of new relevance now. But just to say, there's no particular register assigned to be frame pointer within our current procedure call standard. So if I've got a function and I'm using R7 as the frame pointer, that's what I'm using. If I'm using R11, that's what I'm using. If I'm using R0, I could use that one too, because it's not in the standard. You just have to look at the assembly code and see what's happening. Yeah. Loading and storing from the stack. Ooh, we've done this a lot now, haven't we? Particularly when we did our coding last week, doing some stack hacking to understand how operating systems work. And that's something you'll do in week 12 again, doing a bit of stack hacking, getting up in the stack, finding a value and taking it back out. And you'll have seen that in your C lab about how the C compiler constructs a stack to store local variables. So you'll now be very adept at stack hacking, I'm sure, or you will be at the end of this week, and you'll understand all of these things very well. The storing things in the stack. This is the manual push, right? You're storing something in the stack and then subtracting the stack pointer by 4. Doing that in one line can be done in those 3 different ways. This is the pop operation, loading something off the stack and then incrementing the stack pointer by 4, and a one-liner to do the same thing. Push and pop illustrated. Before your stack pointer is here, that means that wherever your stack pointer is, you can assume that everything above that is used, including the cell that the word your stack pointer is pointing to. Then you store your data in that new area and you move your stack pointer down. So the stack pointer is always pointing to the last used word on the stack. And then to pop, you read your data off and you increment the stack pointer up by 1 word. And you just leave that data on the stack. You don't have to erase it or anything, it just stays there. Moving the stack pointer up is the definition of erasing something off the stack, because the next time you push, that's going to get overwritten with something new. Passing by copy or reference, here's an Uwe slide for you. Julian's at Uwe Strikes Again. Uwe Zimmer, great lecturer, previously worked with COMP2300, and taught me a lot about lecturing, but doesn't teach this course anymore. I do, so I'm changing it to the way I want and removing Haskell things. But this is a slide from Uwe talking about how by copy, by reference, and how the information flow works. A bit different than the way I would explain it, but basically when you're using a copy as the input or output from a function, you're kind of giving a new copy of the value that you're talking about to that function. So you're copying a value into a register in assembly, then your function can do whatever it wants with it, and it copies its value into a register in the output. If you're passing by reference, you're kind of sending a memory address to your function rather than sending a copy of a value. So you would have seen in the C lab how you can specifically set up the value or the parameter for a function to be a reference or a pointer to a value in memory. And of course in C there's the mechanism to allow you to tell C how big you expect that memory location to be, whether it's a word or an int or a double or a short or a char. And then your function is allowed to read from that bit of memory, and if it's by reference output as well, write to it back. So the original is overwritten. And our stack frame, understanding this was crucial to understanding how we can navigate through nested functions. Global variables, parameters, the return address, saved resources, local variables inside our function call. I had a bit of code, I should post this actually, that created a stack frame for you to navigate. with the frame pointer as well. So the frame pointer is going to point to like the start of each stack frame. Well, actually, I think it would point to just before the return address, because this stuff is saved by the caller as part of the outer function. Oh no, the parameters, yeah, that's not always saved. So it's whatever was left over at the start of the start of each function would be in the stack frame. Oh no, I changed tab. Oh, here we are. Yep, someone's just said in the chat, after we've been working in assembly for a long time, sending a copy of an array to a function seems really inefficient. And yet we do it all the time in a high-level language, don't we? Making our compiler and our operating system copy memory all the time. Here's a recursive function, factorial function. I'm not going to make you do any coding in the exam. So some of the previous exams that have asked you to write a recursive function, don't expect one of those this year. Sorry about that. If you really want to write a recursive function, you'll have to just do it for your own fun and post it on Piazza for us all to see. But broadly speaking, the recursive function was really testing how you would understand how to manipulate functions and use the stack in a very basic way, just doing a few pushes and pops, because you have to push, for instance, R1. In that case, it was where you were storing the saved value of your recursive function. And you'd push it onto the stack while you do the next case, the n-1 case. So in this function, we're trying to make our factorial. So if we take in 5, n equals 5, it's in R1. Why would I assume that it puts in R1, not R0? I don't know. And we want to calculate 5 times 4 times 3 times 2 times 1. So we push our n, which is going to be 5, is going to go on the stack. Subtract 1 to R1 and do it again. Then we're going to push 4 on the stack, push 3 on the stack, push 2 on the stack, push 1 on the stack. And eventually we get to 1 and it says do the base case. And the base case, where is that? Oh, down here. We move 1 into R0, our return register, and continue back. So then we get our 2, and we emerge here. So we pop R1, and then we multiply R0 by R1, store the result in R0, continue, pop back here, we end up here, we've wiped off that. Now we do 3, so we're multiplying 3 times 2, we get 6, wipe off that, do it again, we pop off 4 in R1, we're multiplying 4 by 6, get 24, and get back here, pop off 4, and get 5. So what are we up to now? 6 times 2 times 3 is 6, times 4 is 24, times 5 is what? 120, I think. We get 120 R0. We get to the continual code, and we're actually at the end of the recursions now, and we move on. So to do a recursive function or answer one of those recursive function exam questions, you had to be able to, first of all, correctly structure in your head what a recursive function was, and I hope that hopefully your experience in first year would have cemented that for you. And then secondly, you would have to work out how to use push and pop to get that save those values in between function calls, which was a little bit tricky for some folks. It was also incredibly time consuming and tricky to mark, so we're not going to do that one. I learned my lesson about marking with recursive functions, because there's a lot of ways to get it wrong, I suppose. makes it tricky to mark it. Control structures. You should know this stuff really, really deeply now. Oh, and here's my big list of of conditional codes, and you can see we've gone through most of these, but there are a few that use multiple, have little combinations. So make sure that you understand those ones in particular, because they are the more tricky of the list to get your head around. Someone's asked me about marking. Couldn't you just run the recursive in assembly and see if it works? No, we don't actually do that for exams, because whether it's supplied as text or handwritten, in an exam I would forgive small errors. And if it doesn't work, I'm stuck with knowing how many marks to give you. So I can't just give, if I had 10 marks for a recursive question, write a recursive function, I can't just give everybody 0 if it's broken and 10 if it works. I have to work out as a marker every mark in between that. Which ones get 2? Which ones get 4? Which ones get 6? Which ones get 8? Which ones get 7? So it's really about seeing the structure of it and seeing how much you understand about how recursion, how functions, and how the stack works, and how assembly works. And that's better to do by sight. But the problem is, when you grade a recursive function like that, you'd have to compile it in your head and try to run it, which is a huge hassle and unpleasant to do. Yeah, so think about my problem when you're doing your exams. Make it easy for me to give you full marks. Do everything perfectly. Our while loop components, you remember how to do these. Just some different examples of how you would turn standard while loop constructions into assembly. So something like this: while register 1 less than 100, register 1 equals register 1 times register 1. We had a gallery. I don't know why I've got that slide there. Oh yeah, the reason was I had the 3 important components of a loop. We had an expression, we had a Boolean condition, that's the less than here, and we had the code inside the loop. So every structure has these. And when you're writing a conditional expression or an iterative expression in assembly, you have to be clear about which bit of code is each one of these components. And we had this control structures gallery, the sort of nice ways of doing the 3 classic control structures: if then else, and for, and while. And then there was written in a bit of a weird way on this slide. It's better in the original slides I showed in week 4. But make sure you practice a few different loops just to make sure you know how everything works. Data structures. We're now in week 7. I'm going to just take a 2-minute break to have a glass of water. So just hold on to your hats, folks. I'll be back with you in a minute. I know it's an epic day getting through all of these topics. I'll be back shortly. And I'm back. I hope you enjoyed the interim stream music. I think that's only the second time that I've used the break in the lectures this semester, which is, I don't know, interesting. Do I teach 2310 next semester? That's a really good question. I do not teach 2310 next semester. I know that I'm on programs and courses as being the course convener, but I'm also on programs and courses for the course as the course convener in a different. While I'm here, I'll just restart Firefox. Apparently, I need to. Give me a second. I'll restart Firefox. And I'm back. I'm actually teaching definitely, well, I guess not definitely, but I very much expect to be teaching 2 courses next semester, and neither of them is COMP2310. And I do apologize if you would love me to teach COMP2310. You will also love your lecturer for COMP2310, who is Shoaib Akram, who's been teaching Engineering 2219 this semester. Wonderful, wonderful teacher, really knowledgeable about computing architecture and an absolute systems computing mastermind. So you will love COMP2310, really exciting course. I am teaching a course called COMP1720, Art and Interaction Computing. I'm also teaching a small course called Laptop Ensemble, a collaborative course in sound and music computing. So if you want to do an elective next semester or next year, this coming semester will be under COMP3710. It's a 3000 level course, and we make music with computers. And the final exam for this is a gig. So it's a wild sort of course with a different kind of knowledge about computing. That's not that wild, but it's exciting. A different kind of work for you. So if you're looking for an interesting challenge, something a bit off the beaten path, come and do Laptop Ensemble with me. If you want 2310, well, many of you will be taking 2310 as it's a required course, obligatory knowledge for your Bachelor of Advanced Computing. So I'm sure you'll have a wonderful, wonderful time with Shoaib. Back to the content. Here we are. Data structures, main topics, arrays, the structure of arrays, alignment of arrays, addressing arrays, iterators over arrays, and copying arrays. Structures, not structure of arrays. I made a mistake on my slide again. Structures. I should write struct. Where's my red pen? Struct, like you did in C. Because you would have seen in week 10 how what you thought was a record or a structure is this thing in C called a struct. Very simple data storage thing. This work will definitely be in the exam. Definitely in the exam, start, because it's new. We haven't done it before in the midsem. Here was an array. Pretty simple, right? You've got some memory starting at 0x2 7 zeros, and it was an array of words going up, and each 4 bytes you had a new thing. And that's it, that's arrays. Easy. Of course, there are some practical concerns. How do we know how big an array is? Is it possible to write outside the bounds of an array? How can you make an array so that the size can be changed? A mutable array. How do we address a particular element? All of these were specific practical ideas that could jump up and bite us if we're not careful when programming arrays in assembly. A somewhat different look of slide. This is an UVA slide actually. So For some reason this array is going down. I don't know why. This was Uber's way of taking x as the base address for the array. ES was the element size, so the address of the first element is x plus 0 times ES. The first element, x plus 1 times ES, x plus 2 times ES, x plus 3 times ES, etc. So a few questions around here. What happens if the array bounds are violated? If you just write something after the end of the array, well, nothing happens. The CPU is not going to stop you doing it unless you have memory protection set up. It's who is checking for the array bounds. It has to be you. You are checking. You're the programmer. There's a lot of responsibility rests with you when you're programming in bare metal assembly. We had some little exercises adding up all the numbers in an array. We made a register called the accumulator to add things up into as we go. Stored the element size, and then did some quite simple arithmetic to generate our array index memory addresses. You would already have practiced this in an exam situation in the quiz, because the quiz had a question about arrays, which was a question from the 2020 exam. And I know a few folks found that interesting or challenging, but it was a genuine question. So that was good practice in the kinds of questions I ask in an exam about arrays. Records. And we had a lot of fun making a record for a character in a game who had some HP and some mana and a name. So you remember that we ended up doing this in our C lab, or I'll just bring it up. Labs, C. If you haven't done this already, do it now, because we were making something for a student, which looks a lot like that bit of code there. We had a structure which had a UID and a score and a first name and a last name, and each of these were 20 character arrays of 20 arrays of characters of length 20. So you could make that into, you could make that into a structure. And the cool thing about the structure is that once you've got them and you know what their, or the record is once you've got them and you know what their structure is, you can access things by the offset. So you could access the HP was base address, if B is base address plus 0, here is going to be B plus 4 for mana, B plus 8 for name, and then you could calculate which, 2 times 1, so each character in the name is 1 byte. So you could try to access the third character by finding 2x1 plus that. So once you've got this formal structure for a bunch of data, a group of data, you can easily access the bits of it, no matter what that base address is. Records, yeah. Hopefully something folks found useful during their assignments. So I'm looking forward to seeing the assignments. I guess I'll probably tune my ideas for the final exam based on how people go in the assignments, because I want to support your knowledge, maybe examine a few of the gaps, but also figure out what you've learned in this course and make sure you've really learned it from those assignments. So I'll use the assignment or the general vibe of what people did in the assignment to help guide my questions. What's the difference between an array and a record? Well, that's a fairly obvious question. Array is sort of same thing many times. Same thing many times, like if you've got an array of characters or an array of strings or an array of numbers. And a record is different things one time. Of course, you can have an array of records. No problem with that. Back to our big map. Where are we? Tick, 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 tick. So we're now in the interacting with the world zone. I've only got half an hour to do it. We might be a little bit over time today. Asynchronism, interrupts, and concurrency. Now this was where stuff started to get interesting, wasn't it? Remember our big lecture on a Sunday afternoon? Oh, it was a Monday public holiday, I think. Getting to grips with interrupts at the start of week 8 so that you would understand how to press a button on your microbit. And that was a wild lecture. One of my favorites in this semester, actually, was the interrupts, the first interrupts lecture. But it's where the course really starts to heat up. So it's stuff that you will be probably still working through some of that lab material until last week, because it was required for the assignment. So make sure you really understand it. It's still tricky. Asynchronism, main topics, async. Things that are happening at different times is basically what this week of work was about. The interrupts and exceptions idea, when and why, what happens during an interrupt, how is this related to parallel computing or multi-processing, concurrency and synchronization, how do you handle multiple programs happening at once, race conditions, mutual exclusion, and synchronizations methods. Basic synchronization. You do more of this in 2310. So it was a preview of 2310. What's an interrupt? Why are they necessary? That was the basic premise of that part of the course. Having done assignment 2, you should probably have a few ideas about the times that it would be a good idea to use an interrupt and times where it wouldn't. It's certainly possible to do assignment 2 without interrupts, but it wouldn't have been much fun, and it would have made your program very unresponsive. I guess it's something you could tell me why in the chat, or why you think it was really necessary to use interrupts there. Now remember that an interrupt is a line, a wire wired directly into a CPU. And doubly remember that on my replica 1, where is that? That little beastie here. On the replica 1, there it is, an interrupt was one of these pins, right? It was literally a pin connected to the CPU, connected to a pin of the CPU, going in there, connected to the sequencer or the decoder, triggering something that would happen. And remember on this one, there are exactly 3 interrupts: reset, interrupt request, which is like, I'd like to have an interrupt now, which the CPU can ignore, and then the non-request interrupt called non-maskable interrupt, which is a sort of mandatory interrupt. Oh no, I can see all the way through it because it's green, transparent. I'm sure it's pretty funny looking. I'll see it on the video later. I love that I got to do that demo with the Replica 1 with you, by the way, and build it into the course. It's quite fun for me to do something which is very modern, the microbit, and then do something which goes all the way back to the past, or facing the left, which is the direction of the past, all the way back to the distant past of computing. The early 70s, when that chip came out. Interrupt handler. So what is an interrupt handler? A normal function, but it's called when an interrupt is triggered. And remember that once an interrupt is triggered, which occurs, it occurred there, the CPU automatically puts a bunch of stuff onto the stack for you. PC, the flags, R0 to R3, R0 to R3, and then the handler has to do some work to save the callee save variables. I'm not sure if I got exactly the right stack construction here for what the interrupt system on the microbit puts on the stack. You'll know more about it next week once you do your OS lab, because you have to get into that inside the stack structure, inside an exception. I'm saying interrupts here, but I'm also meaning exception, because that's 2 words often meaning kind of the same thing on a CPU. Yeah, okay, and remember that in this instance, LR here had a special value. So it doesn't actually, LR doesn't refer back to the code, the original code that was running when an interrupt occurred. it has the special value. Its basic value is this one, F, F, F. This is probably my head. The basic special value is F, 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 F9. And that's the special value saying return from interrupt. On the 6502, there was a special RFI, it was a special assembly instruction, return from interrupt. So you didn't have that special value system, you had a special instruction to do it. But you can actually use this special value here. There's different versions of it. There's one with a 1, one with an A, a D or something. You can look in the manual and see the different versions, but if you are writing an operating system, as you will in this week in labs, you can use the special number there to return to a different stack. You can have a stack which is only for the operating system or the handler to run, the handler stack and the process stack. So you can keep track of 2 stacks simultaneously and use the interrupt system to switch in between them. Tricky stuff. Context switching. So this was how we use interrupts to switch between 2 programs and give the illusion of running 2 programs simultaneously. The trick here is that when we enter our assembly interrupt handler, which we're going to give the special name dispatcher, or which is going to say which process gets to run at which time, the dispatcher saves up your stack pointer and loads in a different one to allow us to load a different program. And the dispatcher will have its own stack, probably, own stack somewhere else. So this allows us to switch the brain. Like you're opening up the head of your microbit, putting in a new brain, putting the head back on and saying go. And it just starts off the task it was doing from the other program. So it's something you're going to explore practically this week. I won't say too much more about it. You will do more learning. But go back to those lectures in week 8 if you're confused before you start this week's lab, if you have time. This is a really important lab to do. I hope folks make the most of this time with their tutors in the last week. What sort of problems can occur when running concurrent programs? What are the possible solutions? And remember, we had this problem I posed to you called the too much milk problem. So the problem was that you had a fridge and inside there was potentially a bottle of milk. And there would be one roommate A gets home, and roommate A opens the fridge, and if there's milk there, they're fine. If there's no milk there, they go get milk from the shop. So there's no milk there, so A's gone to the shop to get milk. And B gets home, and B looks in the fridge to find milk. No milk there, so B goes to go to a different shop. They have a different preference. This one's gone to Coles, and this one's gone to Aldi, not Coles. I want a short word. Woolies is too hard to write. So A has come home with their Coles milk, while B is still out there looking for milk from Aldi. B comes home with their milk. They've got milk in their hand. They open the fridge. There's already milk in the milk spot. Too much milk. So the too much milk problem is breaking down into a very simple way the issue of shared resources when you've got 2 programs running on a computer. One of the classic shared resources from the history of computing was a printer, because programs back in the old days, people would need to use printers all the time because old school computers, mainframes, etc., they would be printing out what their program is doing and not displaying it on a screen. Like, people didn't have very many screens. They weren't around very often, and they weren't available to most people. So if you were programming a mainframe, you would have programmed it on paper, turned it into punch cards, given it to the computer operator, and they would give you a printout of what happened in your program afterwards. So no screens. You can't view this stuff or edit it on a screen. But even if your mainframe computer could run 2 programs, only one of them could use the printer. So that would be a shared resource that other programs would have to wait for. I don't really know how this stuff worked in more detail than that, but I know that a classic concurrency problem was really related to how we help multiprocessing mainframes use printers. very related to the too much milk problem. In a modern environment, we're really thinking about the fridge not being a printer, but being a cell of memory. So some memory. Program A would like to use that memory to store something, and so would program B. And the problem is that in this context switching environment where your computer's brain can be switched between two programs simultaneously, program B will never know, or it's not easy for program B to know if there's been an interrupt occurring and program A has been at the memory at the same time as program B. So there's no way for B to prevent that interrupt occurring, really, particularly if there's an operating system. The individual processors don't have very much privilege. They don't have the privilege to stop interrupts occurring. They can't say to the operating system, please don't dispatch me out of memory. I want to keep running. I'm very important. They're not allowed to say that. That's not how things work on a modern computer. So we have to have some kind of special hardware support to allow B to know if someone's been in their memory and to recover from it. And so we have a certain way of doing it on ARM chips, and there are other ways of doing it in other hardware systems. You'll learn next semester in 2310, if you take that, what the higher level constructs are to apply the low level systems, which give you more control over synchronization and concurrent software. That was a long lecture. But the basic idea of the race condition is that if you've got some bit of memory, for instance, it's called count in this instance, there's the bit of memory. These are two processes running simultaneously or switching in and out. One process wants to load up the count from memory, add 1 to it, and then store it back. This process wants to load up the count, subtract 1, and then store it back. So the issue is, we could be here in program B, and there's an interrupt. Program A starts running, changing that value in count, and then going back here, and then program B is not going to know that it needs to load count up again. So it's going to ignore what program A has just done. This is A, and this is B. So the value of count in this code is really unknowable if we have the capacity for the CPU to switch these in and out. Look at all the places that can be switched in and out. It can be switched in and out there and there. I suppose that's the only two places that really matter. So this we could call the critical section. I suppose it could switch in and out there and there here. It can also switch in and out here and here in program A. So we could do this line of program B, this line of program A, this one, that one, that one, that one. They could be exactly interleaved, or they could be like 2 each time, or they could be 3 each time and it works properly, or 2 of one of the other, 3 in there. There's many ways for this to get completely and irrevocably messed up, which is why we have methods of dealing with it in our hardware built in. So, the critical section. This is the bit we don't want to run over. We don't want to allow, or we don't want to let context switches to occur during here, or if they do occur, or we can't stop them occurring. If they do occur, we want to know about it and we want to recover from it. So the rules of this is called mutual exclusion. Mutual exclusion is defined to be a method to stop programs changing things in a critical section if they get switched in and out of memory. Ensure that only one program uses a shared resource at one time. You can imagine in the printer case, what if one program wrote one character on the printer and the next program wrote the next character, right? Everything would get completely messed up. Shared resource at once. So we have to have some method of negotiating who's going to go first, do the critical section, and then say, okay, I'm done. And ARM v7m gives us these load exclusive and store exclusive instructions, which basically give you an indication when you get to the store. Program B, getting into our example before, if we get to the store, Program B will know after doing that whether the store has been successful, and it will only be successful if there hasn't been a context switch in between. And we know that because when the literx exclusive load happens, if it sets a exclusive bit in the exclusive monitor, and the exclusive store will only succeed if that bit is still set. If there has been a context switch, the bit will be cleared. It's always cleared during a context switch because it's always cleared on an interrupt, which is how context switches work. So it's a very simple mechanism in ARM v7. A clever way of dealing with this so that you don't have to use literx and storex in your code, a clever way of dealing with it would be to have some kind of lock variable. So in this case, we've got R3 being the lock, and only one of these programs is allowed to unlock the code at once. This is sort of like if program A was opening the fridge and saw the milk, when they go to Coles, they put a padlock on the door and they have the key. So they've gone to Coles, and when they come back, they unlock the fridge door, and then B is sitting there waiting. No, I'm going to wait until the fridge is unlocked before I check for milk. A comes back, unlocks the fridge, puts the milk in, closes the fridge. B opens the fridge, says, oh great, there's milk, and doesn't do anything. So the too much milk problem has been solved with a lock, which is a very, very useful concept used in higher level systems for concurrency, which you'll learn about next semester. Week 9, networks. We had a couple of these sort of high-level topics: transmission mediums, communications protocols, packet switching, circuit switching, simplex, duplex, topology, parallel and serial, and then some information about how you time these things out and use synchronization, and the OSI reference model with 7 layers, all those layers there. This is the kind of thing where I've frequently in the past asked questions like, okay, you're stuck on a desert island, what transmission media could you use to send a message for help? And please design a network protocol and explain to me what its topology is, whether it's serial or parallel, and what its properties are. So asking you to use this knowledge about the details of networks, medium, protocol, the switchedness, simplex, duplex, topology, parallel, serial, all that stuff, make something up and apply it to a crazy real world situation. And you know a lot about timing now because you did it in your week 10 labs. Remember, week 10 lab is part of lab pack 4. If you haven't done it, there's still time to do it before you get to the exam period. So very important to finish that lab work off. What is a communications protocol after all, right? Why would it be needed? Explain your answer. These are the kind of questions where I need you to give me a lot of detail on the exam. So make sure you do a lot of explaining, give me details, and make sure you answer every part of the question if I'm asking multiple things. Topology was the way that nodes in a network are connected to one another. So you can have this bus topology where they're all kind of connected to one line. It's got a line there, which is sort of reminiscent of the physical way this would work, but it could also look like this, right? That's still a bus. It looks like a star, but a star is a star because it's got a node in the middle. This is the same topology as having a line there. There's an old joke about topology from maths, which is, to a topologist, what's the difference between a cup and a donut? And the answer is nothing, because they have the same kind of abstract shape, right? A topology in maths is often considered about like holes in objects, and you can't make a hole disappear. And the cup doesn't have a hole, it's got a kind of pit in it, right? But you can kind of make a bucket and a sphere have the same topology, because the sphere you can kind of just squish in one side until it's convex and makes that shape. But a hole you can never get rid of. You can't shrink a hole and make it disappear. So a coffee cup and a donut are topologically the same. Hope I didn't confuse you there, but it's just an old joke. The bus here has this single line because in a bus network you'd have like one line going around the office, and every computer kind of connects onto that line and can use it in the same way. A ring network, every computer has an input and an output that possibly are both, and they connect around the ring. And a star network, every computer connects to one central source. Someone messaged me, I think. Nope, someone else. One of the tutors messaging me a mistake in lab 12, so I better fix that before tomorrow. Serial versus parallel. So serial is what you've experienced in lab 10, sending one bit at a time. So you've got fewer bits per signal, but it's a bit simpler to set up. In parallel, we often send multiple bits simultaneously, multiple wires, needed to keep communications in sync. So this one it can be a bit tricky. It's often parallel stuff often used in short distances. We've got a lot of little wires that need to be all connected together. Most of your kind of network connections are serial between computers, and all of your connections between your computer and its peripherals. Universal serial bus is a serial connector. In old 2300 or previous years, we often did a lot more parallel systems because we had this board which had a lot more holes, so we could plug in the other board with several wires to make a little parallel connection. In this year's 2300, because our boards have less points that you can alligator clip to, we've tended to use more serial connections in lab 10. So you should be more comfortable with serial now, and particularly looking at those, the lab and the demos I gave you in week 9 about how it works. Here's our explanation of UART. Go back to lab 9 and watch me do those demos with the oscilloscope. That was really, really fun to do. I hope you enjoyed it as well. Remember that there's broadly speaking 2 types of serial connections. One is where you have an agreement between the 2 ends about how fast the bits are going to be occurring. That was this kind of universal asynchronous serial connection, I mean. So when the computer sees a start bit, it starts the stopwatch and starts counting in the bits coming in, and then it sees the stop bit and it waits for the next signal. With an asynchronous connection, like SPI, you would get a separate clock line that is instructing the receiver on when to read the bit. So on the upstroke of the clock, the bit is set. The upstroke of the clock, it reads a bit. On the downstroke of the clock, the bit is changed to the next one. So you can go back to the slides about SPI to see how that works. And then the OSI network layers. Go back to your week 9 lecture. This is one of those things that's very important to understand. Typically there is a question in the exam about it because it's one of the few times I get to examine you on this stuff. It's a conceptual model. It's theoretical. It's not used that much in the real world, but it governs a lot of the way that we can conceptualize how networks work on computers. You will have noticed in your labs and in your assignments really how much of a mess things can turn into when you have to implement everything yourself. So a conceptual model like this says, okay, someone's going to be responsible for the physical link, someone's responsible for the data link, someone's responsible for the network, a different part of your software is the transport, a different part for the session, a different layer for the presentation, a different level for the application, and all of these levels are going to have separate parts, and they could be made by different manufacturers or different teams. Some levels could be part of the hardware spec, which are a standard for everybody, which is great, right? Because this means that if I go to Officeworks and I want a router, I don't have to buy a router that's the same brand as my computer. Any router works, right? I don't have to buy network cables that are the same brand as my computer. And it's not outlandish that this would happen. Like, there are some kinds of computers that do require special wires for some things, Apple, but sometimes there are ways to use standards to eliminate the need to have things locked to particular manufacturers. We can make a standard that works for everyone. And it's actually kind of cool now that everyone in the world has the same kind of Ethernet cable in your house, right? And all of your routers, no matter what kind of router you have, it can usually use any Ethernet cable and work out the maximum speed it can use with that cable, even though there are many speeds possible, right? 10 megabits per second, 100 megabits per second, a gigabit per second, 10 gigabits per second. All of these systems are well known, standardized, and your systems can work it out, which is a great thing. So the concept of network layers is important because it has allowed us to have these standards coming into play. Look through the week 9 lecture for the details of what each of those layers does and where in your program it will be useful. Question. Or a thought. EU is trying hardest to stop Apple from special cables. Certainly is, yeah. And, you know, Apple's got their reasons. I don't know if I agree with them. I particularly liked it when we had Apple computers just moving to only USB-C. And I feel like ultimately they will end up having everything on USB-C again. Yeah. But I'm thinking more about, when I say special wires, like even USB-C wires or USB-C chargers that have special voltages and stuff. It's frustrating when you have to buy a particular manufacturer's charger to get something to work. And I found this on my Nintendo Switch recently, a USB-C device, but it needs the 15 volt standard for a USB-C charger. Do you know which USB chargers supply 15 volts? None of them, like, except for the Nintendo one. So if you want a charger for your Switch, the other chargers work, but they don't work with the dock. So if you want a charger for your Switch in its dock, it has to be 15 volts. Crazy stuff. Now where are we? Operating systems, week 10. Concepts of operating systems, categories, architectures, processes, understanding what a thread is and what a task is in an operating system. Understanding scheduling, and why do we need operating systems anyway? Well, I think you'd probably know why we need operating systems now, having had to do a lot of bare metal programming on your microbit. It's a pain if you have to implement everything yourself. And I think that there were folks starting to want to use a lot of memory and saying, oh, is there some way I can like get the microbit to like give me some free memory? And normally in an operating system, there'd be some kind of malloc, memory allocator system of whatever type, which will provide memory for your variables. But on the microbit, there's no operating system, so you have to do it yourself. Anything you want, you have to do it yourself, which is really a pain eventually when you get to doing high-level stuff. There were two main roles for the operating system in our lecture. One was this virtual machine. That doesn't mean it's virtualized. It means that it's just providing kind of a fake safe environment for software to work in, so that your software thinks that it's got access to memory, but it's really only got access to a certain part and it can't accidentally write on someone else's memory. It thinks that it can talk to hardware by itself, but it's really going through the operating system. It thinks that it can do or that the operating system handles all of the processes so that individual programs don't have to deal with it, and it makes it easy for programs to speak to each other, which is really cool for those programs. It means that the programmers have to do a lot less work, and programs can typically be interconnected. The operating system also coordinates resources, so it's taking care of that shared resource of a printer or memory or mass storage, all these things that only one program can work with at once, and making sure that it passes out access to these things as needed and with certain limits. We talked a bit about the kernel, the core part of an operating system. So it's a program which performs the core roles of the OS. And for all your software running on your computer system, everything you write, all of that stuff has to access the CPU, memory, and peripherals through the kernel. So if you want some memory, you have to ask the kernel. If you want to print out a page, ask the kernel. Play a sound, ask the kernel. It's in charge of everything. So you don't want the kernel to crash. And one of the ways we stop kernels from crashing is we provide some level of modularity within a kernel. So the typical design is to have a kernel that has some modular parts, and if one of the modules goes wrong, your kernel can continue working. Another more dramatic design is this idea of a microkernel, which is even more kind of modularized and separates things out into a more modular way so that it's even more protected from things going wrong. And as we spoke about in week 10, there have been predictions over time that microkernels will be the way of the future. Hasn't happened yet. Who knows what happens in future, but it's an interesting idea to study for further study in operating systems. Why are kernels and user programs separate? How are they different? Aren't they both programs? They are, yeah. How are they different? They have different roles. So it's important within a computer to kind of define which concerns belong to different programs. And why are they separate? So that if one crashes, it doesn't take down your whole system. So we started to define the idea of a running program in memory, a running program. So this included code and the state or context, all your registers and flags, memory, or the memory that was used, permissions or privileges that the operating system defines, and some other resources potentially. There was a difference between kind of the operating system privileges and like hardware privileges. Because as you recall from last week, we explored how on the Cortex M4, there's really only two layers of privileges, like privileged and not privileged. So the operating system might be responsible for having granularity between inside not privileged, so that certain programs might be able to do some things and others might not, right? It's up to the operating system to define that stuff. The hardware just provides a very simple model of privilege for the operating system to work with, to start with. And once we have a process kind of all working together, we can have, I guess, start to have fun assigning processes in different ways and moving them around and context switching. And so we talked about how we might map processes to CPUs. You might have one big CPU with lots of what's going on with my mouse? Oh, there we go. With lots of processors sharing different parts of memory, a one CPU per process kind of system, maybe a shared bank of CPUs, and this is more what we use with our current systems. A lot of shared CPUs and a bunch of shared processors which are then assigned in different ways to those CPUs by a scheduler. And in most CPUs that you will have, normal CPUs, they tend to have one big memory space which is shared by all of the CPUs, a unified memory architecture. And there are some CPUs now on the market, I'm thinking the AMD Threadripper, Apple's, what is it called, M1 Ultra, which break this assumption. They've got a non-unified memory model where there's so many CPU cores now that the memory has to get split between the CPUs, And then if you want to move some memory between those zones, there's some extra time required. So software has to be aware of that and work around those limitations. And the last lecture, architecture. We talked about the history of computing architectures, the basic kind of models of memory access, Harvard versus von Neumann, pipelines, out-of-order execution, SIMD instructions, hyperthreading, multi-core computing, virtual memory, and then some interesting alternative architectures. And we went back to our original diagram, the simple CPU. The very simple CPU. Are any of the components in the CPU not necessary? A good question. I should ask you that in the exam. I probably won't, but a good one for you to study. And this idea of a pipeline. So as you know, on your M4 in your microbit, because you've got these different components of the CPU, they can work at the same time. So the code management part can fetch an instruction into an instruction cache, the decoder can decode, and the ALU can execute. And they can do all of this at the same time. So if your code is kind of working in a standard way, one instruction, next instruction, next instruction, you can potentially do three instructions, do one of the three parts simultaneously and overlap these parts. The problem is if you have to have a conditional branch, for instance, the particular instruction you want to fetch might rely on this piece of code or this execution, for instance. That could be an adds. Oh no, it wouldn't be that. This would be like BLE somewhere, and that could be an adds. So this fetch relies on the output of that to determine where we're going next. So even though the instruction might get prefetched after this execution, it might have to start again with the next fetch here, or delay the pipeline somewhat until the address to go to has been kind of decided. We had this kind of framework of multiprocessing as well, where we had like the number of instructions that happened simultaneously and the amount of data that happened simultaneously. So data was here and instructions was here, and that was single, multiple, single, multiple. So our normal assumption is just one instruction, one bit of data at a time. But by multiplying the ALU, you can have single instruction, multiple data, SIMD instructions. Your Cortex M4 has these. There's an instruction that lets you add 4 bytes simultaneously in 2 registers, 4 pairs of bytes, where each register contains 4 8-bit values. You can have, if you've got lots of different cores, they can all run together and have multiple instructions, multiple data. So they can be running multiple programs at the same time, MIMD. And then there's this multiple instructions, single data, which is always a bit weird. No one quite knows what to do with that. But it's in the framework anyway. Hyperthreading is a bit of a weird one because it means that we multiply some bits of the CPU, but not the execution part. So we can have 2 threads simultaneously running, flicking in and out of memory, doing a really fast context switch, but using the same execution units. So all the registers and flags, the decoder and code parts are the same, or the decoder and sequencer are duplicated. The ALU is the same. This is allowing us to do very quick context switching. It's almost MIMD, multiple instruction, multiple data, but it's not quite simultaneous, is it? It's allowing us to hold two threads together and do context switching without the cost. So that's why it's called hyper-threading. Virtual memory. This was an important one for operating systems because it really allows an operating system to do its job properly of providing a safe memory environment for processors. It's something which is not available on your microbit. It doesn't have the hardware to do virtual memory. We've got a memory protection unit. So you can kind of have an operating system, but it would be a limited one on your microbit. And a good question here would be to think about virtual memory from a hardware perspective as well as from a software perspective. Because there are two ways of thinking about it, aren't there? Both the hardware that needs to provide it and its application within operating systems. And I think we're kind of there. We did it. Tick, 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 tick. COMP2300 in the bag. That was a pretty epic journey, folks, and I want to thank you in particularly for coming with me on this particular semester when we were starting with new hardware right at the start. I know you have a bit of work to do still in the course before things wrap up. You've got your final exam, you've got your week 12 labs. I'm still going to be here supporting you through Piazza and that channel of communication. But this is kind of the end of our lectures. So if there's any last minute questions or requests to do anything, jump in. But it's been a big day getting through all those topics at once. And certainly an epic journey. I should have some music at the same time or something so that it feels more epic. I'll get my music in OBS. How do we make that happen? Add media source, I think. Get one. Add existing, BGM. There we go. Turn it down. And this one. Oh, maybe -20 is right. Yeah, so the questions are not exactly rolling in. I thought there'd be more questions. Has everyone gone to their other lectures? Maybe you all skedaddled when I started my break. Well, that's fine. Anything happening on Thursday? No, nothing happening on Thursday. I thought I'd just like to do my last lecture today because there's a lot of topics to get through, but it's nice to do it in one big block. For Thursday, I'm going to use the time to work on your exam. So I decided it was probably enough to do this week, and I'll let everyone have an early mark from their lectures and focus on finishing up your final assessment tasks. So I'm not going to do a presentation on Thursday. Sorry. Any other questions? Well, I guess you don't. I wonder what else I could talk about. It's 16:05, so we're really out of time. Thank you, Tao. Well, I think there's no more questions, so I'm going to turn on the final slide, the outro. Last time for the semester. Folks, it's been a wonderful sequence of lectures. I think we've been through some good times, a few tricky demos, a few curly questions from the live audience and the tutors who've joined me on many occasions. This has been the biggest COMP2300 class ever, by the way. Had really big enrollments, and it will be the most COMP2300 students to complete the assessments ever. Someone wonders how people use peripherals in assignment 2. Me too. I haven't managed to look at assignments 2 yet, so looking forward to seeing that and decoding it a bit. But for now, I might turn myself down. I'll let you hear the outro a few more times. Study well. Catch you in labs. Any more questions, ask me on Piazza. Always here for your questions, except on the weekend when I'm not. I'll give you more information about the final through Piazza. And look forward to seeing your great assignments. So thanks folks for the lecture. Have a good one.